All right, thank you. And thanks for coming to such a heady topic as your last talk of the day. My talk is called In-Depth Ruby Concurrency, Navigating the Ruby Concurrency Landscape, like Mike said. When I first found out I was doing this talk, I told my parents I was doing a talk on Ruby, and they were really confused because they thought I was doing a talk about their dog. And so if you've come here to learn about how to play with my parents' dog Ruby concurrently, I'm sorry this isn't the talk for you, and you may want to leave. So I'm JP Camara. I publish technical blog posts at jpcamara.com, and over the past year I've been doing a series on in-depth Ruby concurrency, basically this topic. I do some open source at GitHub. I'm active on Blue Sky at jpcamara.com, and I'm a principal engineer at Wealthbox CRM, which is a CRM for financial advisors. So today we're going to talk about a group that I affectionately refer to as the Ruby concurrency crew. That consists of processes, Ractors, threads, and fibers. So when I think about Ruby concurrency, I think of it sort of like a nesting doll. Essentially, as you open up pieces of the nesting doll, there's new layers of concurrency inside. And at runtime in Ruby, you can introspect all of those layers really easily. So you've got the process ID that you can get from process.pid, and then you've got Reactors, threads, and fibers all kind of nested within there, and you can access all of them using .current to introspect information about them. So the first thing we're going to talk about at the top level of that nesting doll is the process. So processes are parallel and concurrent, and we'll kind of dig into what that really means exactly. They work in isolated memory spaces, meaning that when you have multiple processes, they're unable to communicate with each other. They can't share memory between each other, so things like class loading and stuff can't be shared between each other. They map to an actual OS process, so you can introspect them at the operating system level. And they're the most expensive form of Ruby concurrency, and we'll talk about that a bit. So we have a very simple example of just fork do here. That'll create a process for you. Very coincidentally, Matt's did a whole section about prime numbers and how we can generate the world's largest prime number. And I happen to use primes here because they are kind of an expensive operation to do in parallel. And by the way, I tried Ruby head with the largest prime available, and 10 minutes in, I just had to shut my computer off because it was just dying under the weight of it. So I wouldn't actually try running this code. You need to make it a little simpler. But basically, I've got 3 ranges of numbers from 1 to that very large prime number, and I'm going to walk over them and create forks and try to figure out what prime numbers are in my lists. And so the first thing you'll see when I run that code is that the fork actually starts running immediately. This is true parallelism in the regular C Ruby runtime. And at the same time, you'll also see I've got this process status command running at the bottom. We've got a new process that got created. So I set the process title to Ruby with the index after it, and then I just start selecting primes from my numbers. And while I'm doing that, I'm getting full CPU saturation. And for each one that I run, until I go to process wait all, and that initial process just kind of goes off and waits, I've got 3 99.9% CPU saturation processes running. At the same time, I mentioned that processes are parallel and concurrent. I think people normally think of just like threads and fibers as being concurrent, but really concurrency, whereas parallelism is sort of running things simultaneously, concurrency is really about orchestrating or composing tasks. And you essentially put those things into a unit of work, you hand it off to something, and you say, run this for me in whatever way makes sense. So for instance, like Sidekiq jobs are a great example of concurrency. And so in our case here, when we first start running, because it's a process, it starts running in parallel. But in this example, we've actually got 5 ranges, and on our weird hypothetical computer, we've only got 3 cores. And so as we start to go beyond the initial 3 cores we have available to us, things still continue to run. Things still continue to switch around, but our CPU usage for each of our processes goes down because they're starting to share those 3 CPUs. And so at this point, we've got 75%. And then basically by the time we get to the end of it, we're running at about 60% CPU. But we're running concurrently, we're swapping back and forth between them, we're orchestrating these tasks. So what's an example of processes in the real world? One of my favorite examples is a newer server from Shopify called Pitchfork. Pitchfork is a multi-process, what's called a reforking server. It maps web requests one-to-one from a web request to a process, meaning for however many processes you have, that's how many web requests you can run at any given time. And if you go over that, then your requests start to queue up. And those handle your parallel CPU and I/O for you. But how do you decide how many processes you should actually use? And for my answer is really ideally as many processes as you have cores. So if you don't have as many processes as you have cores, you're essentially leaving parallelism on the table. Additionally, if you're using a server that only uses processes like Pitchfork does and doesn't use any of the other concurrency units we're going to talk about, you really want to up that process count as well. More like 1.25 to 2 times as many processes as you have CPUs. And that's because concurrency. So when you have when you're only running processes, you really want to take advantage of that concurrency. Some things are going to block on things like I/O. They're not going to be running in parallel on CPU, so you want to be able to take advantage of that and run extra processes. I mentioned that processes are expensive, and one of the things that's most expensive about them is they're heavy on memory. And so in a typical example, you've got your parent process that you're running out of. We call our fork due like we were doing for our prime number selection. Our child processes each have what are called pages of memory. And so those pages of memory are completely unshared between them. But there's lots of things that you could share in your application. You load your classes, maybe you've got YJIT bytecode. There's lots of things that are important to share, but you can't do it here. And so you really want to improve your memory usage by doing something called preloading, which you may have seen before. Preloading basically just means before I start forking, I require some amount of code. By requiring that code in this example here, I'm requiring the Rails application code, and I'm calling initialize. And so if you have YJIT running, you're going to get some bytecode. You're going to load a bunch of your classes, maybe some things that are memoized or initializers run. And that all gets preloaded into my parent process. Now, when I fork, my child processes are able to take advantage of something called copy on write. So there's pieces of memory that may never change in my child processes. They never have to reinitialize them. And so the memory overhead on my child processes goes down because it shares it with the parent. Most servers support a preload option, so you really want to improve your copy on write memory by utilizing that. The most interesting thing to me about Pitchfork is it's got this newer concept called reforking. And so what reforking is basically the parent process creates a child without doing any preloading, and it's called the mold or the template. That template does the preloading, and from here, things start to pretty much look like our previous example. We've preloaded, we've got a few pages of memory that we can use to create our, what we call here sibling processes, but effectively child processes. So we're sharing a minimal amount of memory, we're getting some reduced overhead, we can probably use some more concurrency, and we're getting benefits. Where things really get cool is with Pitchfork, it has something called refork after, which means that after a certain number of web requests, it'll actually fork again from that mold process. And what that means is we've gotten lots of web requests. We've done all our initializers. Memoization may have happened. A lot more YJIT may have happened at that point. All of that stuff is now reforked and able to be shared with a next generation of processes. And so in this case, we went from 3 pages of memory to many pages of memory, a much more warm application, and it continues to do that at different intervals. Here we have 50, 100, 1,000. At Shopify, it reduced their memory usage by 30% and their latency by 9%. So we kind of understand what processes are good for in terms of parallelization and a certain amount of concurrency. What is Pitchfork good for? So if you're currently a Unicorn user as your server, or if you're using Puma without threads, Pitchfork might be a good option for you. If your web requests are primarily CPU constrained, Pitchfork also might be a good option. Or if you just aren't sure if your code is thread safe, you might want to utilize Pitchfork. So the next thing technically would be Reactors, but I'm going to save that for a little bit later, so we're going to come back to it in a bit. So next we're going to talk about threads. Threads are purely concurrent, whereas processes are concurrent and parallel. Threads just have this concurrent concept. They operate in shared memory space, so they don't have to initialize a whole new block of memory every time. They can share the memory of their parent. They do allocate a little bit of memory, but nothing near what a process does. They map one-to-one for the most part with OS threads, and they're less expensive than a process. And so we've got a little example here of thread.new. Now we're going to try to use our same prime example here, and it's not really going to work out so well. And so the first thing you'll notice, as opposed to our process, where our process immediately started running our operation in parallel, nothing really happens here at first. We're seeing our threads actually are getting created at the operating system level, but they're all operating at 0% usage. And that's because of the GVL. You may have seen some previous talks about the GVL. It's this global virtual machine lock that every thread needs to have access to keep the Ruby runtime consistent internally. And so that means our threads can only run Ruby code one at a time. Basically, until some event comes along, something blocks, the thread scheduler switches them. They can't do anything until that happens. And so in our case here, eventually our main thread says, hey, threads, give me your values, which is just a way of blocking on the thread and asking for whatever the last value is that comes back from the thread. We set a thread current name, so we get those Ruby 0, 1, 2 kind of options there, and then we select our primes. But ultimately, we have to just keep swapping back and forth with the GVL, and so we never achieve more than 100% of one CPU, and each thread is operating at about 33% effectively. With that in mind, what are they good for? And they're good for things that block. So they're good for file operations, DB calls, HTTP, sleep, process management. And if you use a library like bcrypt or zlib, those will actually release the GVL as well, and you can operate those in parallel. So each thread waits for the OS response in parallel. So that ultimately means that, to me, how I refer to threads is they're really parallel-ish. Effectively, like if we were to take an example that better utilizes them. So here we're doing a slow report in the database. We're retrieving a customer from Stripe. We're doing another related API call. And then we're still gluttons for punishment, and we're doing more prime number generation. And so in this case, we still have to grab that GVL first. But once we go to a blocking operation, we release it, and those blocking operations can continue to happen in parallel in the background. And so in this case, what ends up happening is we're parallel-ish. We've got 3 additional things running in the background while we're doing our prime number generation in the foreground. So what's an example of threads in the real world? Sidekiq is a perfect example. Sidekiq is a multi-threaded job server. That was kind of one of its innovations at the time. Jobs often block on I/O, so it's really valuable to have threads. They can help you parallelize your I/O. And threads are much cheaper than processes, so you can have a lot more of them. It's pretty simple to express. Jobs essentially run on a thread. They pull jobs from Redis, job information from Redis, and then within your jobs, whenever you do something like an HTTP call or a database call or whatever, those can be parallelized, and so you get better throughput. But how many threads should we use? How much should we allocate? It's a complicated question, but there is one answer. You may have seen some of Nate Berkopec's work where he's talked about Amdahl's law. So we don't really need to understand this formula per se, but we should just understand a couple portions of it. So S is the proportion of our program that can be made parallel, so the percentage in I/O or CPU. And then P is the speed up factor of the parallel portion. So that's the number of processes, Reactors, threads, or fibers that you're going to be running in association with the kind of I/O that you're doing. So we've got this handy table here, pre-computing the formula for you. Basically, at the lowest end, when you're around 10%, you're really not getting any benefit out of threads. You might as well just be running processes. When you get into the more common range of around 25 to 50% CPU in your background jobs, 5 to 10 threads start to help a lot. On the low end, it's about 1.25 increase in throughput, and we get almost up to 2 times throughput. As you get really, really high, that might be something more like you're making just tons of API calls or WebSockets or something like that, but you can get a lot of thread benefit out of that point and a lot more throughput. So what's Sidekiq good for? I mean, you're probably using Sidekiq right now, so you probably know what it's good for, but for jobs that operate with more than 10% I/O, your app is thread safe, which most apps start out that way, so just try to keep them that way. And when you're using Sidekiq, 5 to 10 threads is a safe bet. How do I decide between processes and threads? And the answer is really, you want to have both. And so what's a good example of something that has both? Puma is a multi-process, multi-threaded server. The processes parallelize your CPU for you. The threads more efficiently parallelize your I/O. So similar to Pitchfork, when your request comes in, things can only be parallelized by using processes. There's this Reactor thing for connection handling in the middle, but then we ultimately hand off to our threads, which for something that does, look at those Amdahl's law ranges of I/O, you can increase and tweak the amount of threads you have to benefit your throughput more. So I've thrown this Reactor thing in the middle here. What is a Reactor, and why should you maybe care or understand what Reactors are? So Reactors, not Reactors, sorry little buddy. Basically, a reactor is this loop that runs and interacts with something called the kernel event queue. So pretty much every operating system has this very highly optimized queue where you can say, hey, I have this particular operation I want to run. I want to do some HTTP and tell me when the socket's ready to write to or read from. You can give that off to the kernel, and it can handle thousands, hundreds of thousands of these at a time. But it's kind of inconvenient to directly deal with that, so the reactor handles that for you. You register an event handler saying, hey, when is this socket ready to write to? That hands off to the kernel event queue. You go off and do something else. When it's done, the kernel event queue lets the reactor know. It invokes your handler for you, and you can start writing to your socket or reading from your database. This is the same thing as an event loop you may have heard of, and it's used by tons of stuff. Puma, Action Cable, Event Machine, all sorts of things. It's a really powerful concept, and the only reason I bring it up is because we're going to even use it later on. So what are reactors good for? They're good for the foundation for highly scalable I/O. They're good for buffering requests and for slow clients. So in Puma, it utilizes it so if a client is really slowly downloading or uploading content, your threads don't get occupied. The reactor can handle thousands of these at a time. And for managing incoming connections. It's not the type of thing you may use day to day in your own code, but tools you use will use that. And then what is Puma good for? It's a general purpose web server. You've got a mixture of CPU and I/O. No one got fired for choosing Puma. It's got 404 million downloads. You're probably using it right now. All right, the next concurrency unit we're going to talk about are fibers. Fibers are concurrent, similar to threads. They're shared memory, similar to threads. They are user space in this case, so there's no OS equivalent that we can introspect. It's something that's essentially just managed and created by Ruby. And they're less expensive than threads, Ractors, processes. Pretty similar interface to creating them, fiber.new. No, sorry, buddy. So in this case, we're going to do the same example again. But what we'll notice here is that unlike threads need to have the GVL to be able to run code. But I've got that little thread.main with the GVL acquired already at the bottom. That's because fibers basically run inside of a thread. So they don't acquire the GVL, but they still can't run in parallel. And that's because fibers are actually considered to be cooperative. So fibers can actually jump back and forth between each other. They can yield and resume. They have to communicate with each other and cooperate with each other to be able to be created and run. So at the end here, our main fiber calls resume on all of them. Each one of them runs range.select and yields the value. But all we really get is this like sequential going back and forth between them. It just sequentially runs. So it's not really that useful. So in Ruby 3.0, there came along the FiberScheduler. And so it gives us ability to basically put fibers kind of on steroids. Fibers essentially, they still manage the stack for you because they can still operate concurrently, but we've got the scheduler behind the scenes that will do a bunch of extra operations for us and will unlock a lot more features for fibers. And so if we take that same Reactor example that we had before and we apply it to fibers, and we'll use something called the async gem, which is kind of the primary fiber scheduler implementation. The first thing you do is you create the sync block, which starts a Reactor for us behind the scenes. When you call async there, you're basically just creating a fiber behind the scenes. When we call dbquery, it just looks like a regular synchronous call. It's just the same thing we're used to. But behind the scenes, what happens is the fiber scheduler puts that into a Reactor for us. It registers the event. It then puts us into a list of blocked fibers, checks for available fibers, and moves on. The same thing happens with our stripe call here. Once we get to the end, eventually those operations are finished, our synchronous calls will return, and the fiber scheduler kind of handles all this transparently for us and gives us our result back. So once you have the fiber scheduler, they're good for a bunch more stuff, but they basically at that point still just kind of look like threads. Each operation becomes a part of the event loop in this case instead of being put to the OS in parallel. I'll go through the same kind of parallel-ish example because they kind of get that parallel-ish functionality again at the same time once they have the fiber scheduler. So we do async here, and the difference when we're doing these async calls is they actually automatically go into that background. And so we've got these background processes. They're being put into the Reactor and handled for us, and we can still do our useless calculation of prime numbers. This all seems familiar, and it seems almost kind of pointless to have two things that nearly operate the same way. But the way that I look at them is I kind of compare like the strengths and weaknesses of each. And so for me with fibers, they operate more deterministically, meaning because they have to cooperate, there's very like exact seams of where things can actually happen, where things can switch out, versus threads where you basically can have any instruction swap while you're in the middle of running code. They're lighter weight on memory and CPU. And if you have 5 threads and 5 Reactors, this really isn't going to matter. But as you scale up a server, the scalability of the Reactor goes much higher. The cons is sometimes a big one. It's that they block on CPU. If a fiber starts doing a really heavy CPU operation, there's nothing you can do about it without it cooperatively scheduling another fiber. So what's an example of fibers in the real world? We've got Falcon, which is a multi-process, multi-fiber server built on the FiberScheduler. Like our previous examples, like everything in C Ruby, the parallelization happens from our processes, but then everything else, our connection handling, our request buffering, our parallel I/O, all of that just gets handed off into the FiberScheduler. And so what's Falcon good for? It's good really for any web app, but it's particularly good for high I/O, high connection or proxying web applications. Because of this FiberScheduler and the ability to scale up these connections, you can use WebSockets and HTTP2 really easily in it. I did a benchmark recently against a Node.js WebSocket benchmark, and Falcon was very comparable in terms of the performance, which was great to see because Node.js is a highly optimized environment for WebSockets. Additionally, even without Action Cable, you can kind of just slap some WebSocket functionality into your controllers using Falcon, and it just works. All right, we're finally getting to Reactors and giving them their time to shine. Reactors are both parallel and concurrent. They share memory, but with a more strict interface, which we're not entirely going to get to today. They map to a pool of OS threads, so they're not directly one-to-one, but they do get to utilize threads behind the scene, and they're less expensive than processes. And they're pretty simple to instantiate. So in our case here, exactly the same as when we were demonstrating processes, when we start calling that Reactor new, we immediately start running in the parallel code in the background. So that we can see that behind the scenes, when we do this process status for our threads, we are getting actual CPU saturation every time we create a new Reactor. And once the main Reactor calls take on your Reactors, they can go through their range select, they can find our prime numbers, and then they can yield those prime numbers at the end. They work, but they do need more community support. You still get a Reactors experimental warning at the beginning. There's certain common libraries that because of the strict sharing support, you can't utilize out of the box, which can be a little bit confusing. And there are some API issues that need to be fixed. Is there an example of Reactors in the real world? There are people using them, but in terms of library support, you don't see a lot. But there is a cool library called Mooro. Mooro is a multi-Reactor experimental server. In front of it uses async HTTP, which is that same underlying FiberScheduler Falcon technology to handle connection handling and request buffering. But then it uses Reactors to handle parallel CPU and I/O. So what's Mooro good for? It's really just good for experimentation right now, but I encourage you to give it a look and try it out because it's one of the main examples out there of something trying to use Reactors in a more serious-ish way. All right, that was a lot. What are the actual takeaways for the talk? So the first takeaway that I want to give you is maximize vertical scale. So before you start trying to scale out horizontally, take advantage of everything that exists on your container, your server, whatever. Always take advantage of preload, and if you have the option, use reforking. Puma actually has an experimental feature for reforking as well. You get more space for concurrency and more space for widget bytecode so you can run your Ruby code faster. Match your Ruby process count to available CPU count. And from there, utilize Amdahl's law to figure out what kind of I/O percentages you're utilizing in each of, and figure out how to scale largely your threads from there. So for instance, if you have Sidekiq running, make sure you take advantage of Amdahl's law and understand what your I/O percentages are in your jobs. Because if not, you're just paying for less. And then in terms of a conceptual compression for how to understand which one to use where, I would say whenever you're trying to parallelize I/O within your own code, I would suggest using the async FiberScheduler. The async gem has a really great interface and ergonomics, and because fibers operate more deterministically, it's largely a safer way to write your code and have less foot guns along the way. If you're trying to parallelize something, I would encourage you to use Reactors. There are people out there using Reactors for parallelizing CPU operations within their code. There's also a gem called Parallel, which will run processes for you or threads, but it can also experimentally run Reactors for you, so you could use that as an abstraction. And then otherwise tune your servers and let them do what they do best. So processes for CPU and threads fibers for I/O, and tune them based on your server settings. There were things I didn't get to because I think all of our heads would explode if I tried to do that, but basically there's an MN thread initiative in Ruby 3.3. It's threads essentially backed by Reactor, which I think is a really cool initiative, and it is actually available to use under a flag, so you could try it out today. SolidQueue, which is a server you've probably heard of. It's multi-threaded and multi-process job server, which is really nice. And then just, ideas for a simplified concurrency feature, but maybe that could be a future talk of some kind. And also I do have some stickers of all the Ruby mascots if you're interested. I don't have a ton, and I have more fibers than others. I don't know if that's some sort of metaphor or something for how much cheaper fibers are, but basically I do have some stickers if you're interested in that. You can find me at jpcamara.com or on Blue Sky at jpcamara.com. Thank you.